Electric flux. It's a new concept that you come across in your career, because in the lower classes you won't get such a type of imaginary concept. Flux, this word is a new word to you. Of course, you might have seen what is LUX, lux, F. If you remove F, you know what it is. You are familiar with that word, lux, but this is different. This is flux. What is electric flux? It is a very new concept like this. Now there are different cases or different areas in physics where you get this word flux. You may get electric flux. You may get a word like luminous flux, magnetic flux. So wherever there is field, electric field, magnetic field, the field due to light, everything, we get the word flux. Now imagine a bulb here. Suppose you have a bulb, filament bulb. It emits light in all directions like this. Light travels in all directions from the bulb, three-dimensional like this, and it is switched on. Now when the light travels in different directions from the bulb, you know that the Michael Faraday gave an idea of writing the strength of the field by drawing lines like this, and these lines are diverging from the bulb, and of course Michael Faraday gave the idea for electric field lines, and we draw the rays of light like this for luminous field, and these lines are very close when they start from the bulb, and they move far away and far away as they move away from the bulb. That means, what does it indicate? The strength of the light is stronger here, weaker here. So how to identify it? Just take a small piece of paper, because when light falls on the paper, you can see the paper. Our eyes have the ability of identifying that light. Now when you place the paper here, a small circular piece of paper here, you receive more amount of light, and you can see more amount of light on the paper. If you place the same paper here, that paper receives less amount of light. So the amount of light here and here are more. So won't you just think that it is just because of the reason that if you can assume that many rays of light are coming from the bulb, which you can't see, but actually finally what do you observe is light. It is not the rays. The ray is just a concept. And when these rays of light move away from the bulb, they are crowded when they are just leaving the bulb, and they become far apart when they move away and away. That is what do we say in our day-to-day life. The intensity of light is very strong when you are very close to the bulb, and intensity of light is very weak when you are away from the bulb. That's the simplest way of saying. So now can I say it like this? The number of rays passing through this paper are more here, and the number of rays passing through this paper are less here. That is the meaning of flux. And simply I can put a familiar word to you. Flux means number of rays passing through this, and flux in the sense luminous flux means number of rays passing through this small piece of paper. I will make a general statement. This is not the statement that you are going to write in the exam. You shouldn't write this one. Just for understanding purpose, I will do so. Number of rays of light passing through this small area is luminous flux. I will define it like this. And that luminous flux is less here, it is more here, because as you come closer, the rays of light you will come across more and more. Now, that means the flux through this small surface, small piece of paper, that depends on how close you are towards the source. This is the source of light. Now, is that the only factor which decides what is the flux through this luminous flux through these two small pieces of paper held here and here of the same area? No, it doesn't depend on only on the distance. It depends on the area also. Suppose if I had taken a larger piece of paper, then it would have received more amount of light. That means flux through a small area depends on the size of the area also. So if you can assume that flux is the number of rays of light passing through a surface, then the number of rays of light passing through the surface, that means almost the luminous flux. It depends on how close you are to the surface, one factor, how large your surface that is held is. Now, are they the only two factors which decide the amount of flux through this surface? No, there is one more important factor. In what angle you hold this surface, that is also important. If you want to read the book, you have to hold the book like this, right? You have to hold the book like this in front of the light. Light should fall on the book, and the rays of light should fall normally on the book. Then you will receive maximum amount of light. And if you are holding a paper like this, all the rays of light will pass by the side of the paper. They won't fall on the paper. You have to hold the paper like this so that light falls on it normally. So any paper held like this from the source will receive the light. If the paper is held like this, all the rays of light will just pass by the side of the paper. They won't fall on the paper. So the rays of light simply will trace it like this, and graze the paper like this. That may be the best word. So when a ray of light is passing just parallel to the paper, they are grazing the paper. They don't fall on the paper. So if you place the paper like this, they fall exactly on the paper. So if you have if you have a set of rays of light falling or coming like this, it is the angle at which you hold the paper is also important in order to receive maximum light. So if you receive it like this, you will receive maximum amount of light. And if you hold the paper somewhat at different angle like this, then the amount of light falling on this will be different. And if you hold the paper exactly parallel to the rays of light, no light will fall on this paper. So angle is also important. Now that if angle is important, of course, along with the distance, the size of the paper that you have held, and the angle, all these come into picture when you measure the flux. Angle means either sine theta, cos theta, tan theta, any theta trigonometric function must come into picture when you measure the flux. Now, so if you are, and regarding this angle, I can give you many examples. See, when it is sunrise, when the sun is rising, the rays of light are coming like this, and this sunlight is very pleasant to us because they are falling at a very small angle, at some angle, they are falling at an inclination to the earth. When the same sun is in the mid-noon, directly above our head, overhead, rays of light are falling normally to the earth. That sunlight and that sun is very bright, and we feel much radiation falling on the earth. And the same sun, when he or she is here, the amount of light falling is less, and that is that angle makes us a pleasant light, but the same light will be very burning when it is here. Similarly, during the sunset time, the sunlight will be very pleasant to see. It is as if you have your face like this, if your face is like this, and you are looking like this, and if your torchlight is put into your eyes like this, then they directly hit your eyes. You see the maximum amount of light. And as you turn your face like this slowly, the amount of light falling on your face goes on changing. You can turn your face as well as the torchlight also. You can keep your face here only. Bring the torchlight from this position like this slowly. What happens? The amount of light falling on your face goes on changing. And when the torchlight is directly in front of your face, you receive maximum light. And as the torchlight is turning to the other side, the amount of light falling on your face goes on changing. That means flux, the number of rays of light falling on your face is the surface area now. That falling, the amount of flux passing through your face, or the number of rays falling on your face depends on the angle at which your face is. Now, the same is the case in the case of electric field. Any source charge will create a field around it, and we represent that field in terms of electric field lines. Michael Faraday gave us a way of representing the electric field, and we call it as electric field line. So now suppose there are electric field lines like this. I didn't show you any source charge, okay? I didn't show you any source charge. Source charge is somewhere else, and there are electric field lines. They are parallel and equidistant, so it should be a uniform electric field. Now, imagine a surface here. Here is just imaginary case. You should not have a piece of paper or so. Simply imagine a surface here like this. How these electric field lines are crossing this surface? They are crossing normally through this surface like this. Okay. So, maximum electric field lines are passing over this surface. Now, slowly you turn this surface like this. What happens? Suppose the electric field lines are like this. They are uniform electric field lines. Now if you turn the surface like this, then the amount of light falling on the surface goes on changing, and when the surface is exactly parallel like this, if you hold a surface like this, then no electric field line will pass through the surface. So if you hold the surface like this, you can get maximum electric field lines. When you turn it like this, the number of electric field lines crossing the surface goes on changing. When the surface becomes like this, no electric field line will pass through the surface. It will just graze the surface. So orientation is also important. Now how do you form a formula to measure the electric flux? I'll change the paper. Okay. So formula for a electric flux. So now you should have a definition for electric flux, and you should have a mathematical measuring formula. Electric flux. Yes. So I will define the electric flux like this. It is the number of electric field lines passing normally through a given surface. Sir, why do you call it as normally? Every time the electric field lines may not be passing through a surface perpendicularly. So how do you call it as normally? Even though they are not falling normally, you get the component of that electric field falling normally. For example, suppose I hold a surface like this, and if its normal is in this direction, but if the electric field is in this direction, electric field lines are crossing a surface like this, say. Yes, some charge is kept here, say positive charge, and its field lines are shown like this, and electric field is moving like this now. This shows that the parallel equidistant lines indicate that the electric field is uniform everywhere, and the normal to the surface is like this. Now how much angle does it make with the electric field? It is making an angle theta with the electric field. Now get a component of electric field along the normal. So if electric field is in this direction, normal to the surface is in this direction, can't you get a component of this here, that is E cos theta? You can get it. Now that means if the orientation of the surface is also a factor which decides the flux through it, number of electric field lines passing through it, then area becomes a vector here. If delta S is the area of this surface, you have to treat it as a vector because its orientation decides the amount of field lines passing through this. So your what is the angle at which your face is present towards the light, whether your face is directly in front of the light or whether your face is making some angle, that decides the amount of light falling on your face, means your surface area of the face is also a vector. Sir, what is the direction of that area then? Draw a normal. Normal to the surface is the direction of the surface area. So now treating surface area as a vector, electric field as a vector, and we want E cos theta. So you go for dot product. You know that A dot B is AB cos theta. So I will take a surface like this of surface area delta S, and its normal is in this direction, and electric field lines are passing like this. You know that if this is completely parallel to the surface, no flux will pass. That you know it. So normal to the surface is like this. That is the direction of surface area. Suppose this is theta. Then how do you define flux? The small amount of flux passing through this small area. Since this area is very small, I will use delta term. You know what is delta. Delta x, small amount of displacement. Delta t, small amount of time. And delta capital T, small amount of temperature. Similarly, delta phi. Phi is the unit, symbol used to represent electric flux. Phi is the symbol. So small amount of electric flux, the number of electric field lines passing normally through this surface area is delta phi. Then delta phi is equal to, it is the dot product of E and delta S, where E is the electric field vector and delta S is the area vector, and area vector is along the normal to the surface area. Okay, so you know that here is a vector, here is a vector. The dot product of two vectors, answer is a scalar. So flux is a scalar quantity. It has no direction finally. Electric flux is a scalar quantity, it has no direction. So can I write it like this? Delta phi is equal to magnitude of A, magnitude of B into cosine of the angle between them, because A dot B is equal to AB cos theta. Magnitude of A and magnitude of B into cos theta. So cos theta comes into picture. Now suppose this surface was exactly normal to this electric field. That means normal to the electric field and the electric field lines are parallel. Surface is normal to the electric field lines. That means normal to the surface and electric field lines are parallel. Then this would have been cos 0. Cos 0 gives highest value. Cos 0 is 1. So you get maximum flux passing through this surface. Right? Suppose the surface was held like this. Electric field lines would have moved like this. No electric field lines would have passed through the surface. All of them might have grazed the surface. Now normal to the surface is like this, and electric field lines are like this. Theta is 90. Cos 90 would have made all the formula to 0. Delta phi is 0. So flux depends on the orientation of the surface and depends on the area of the surface, depends on the distance where you hold it. If you move away and away, the electric field, if it is diverging electric field lines, then the flux will go on decreasing. So that distance comes in electric field formula. You know that it is 1 by 4 pi epsilon naught q by r squared. So you get it in this formula. So distance, area as well as theta. I can give you another good example for why that angle decides. Suppose you have a pipe like this in which a large amount of fish are moving like this. Fish are moving like this, moving in the same direction. Water is flowing in this direction. If you want to catch the fish, what you have to do is you have to place a mesh like this. You have to place a mesh like this here. If you place a mesh like this, all the mesh which should have the holes which are smaller than the fish, all the fish get trapped here because every fish has to pass through the mesh. Whereas if you place the mesh like this, what is the use? No fish will pass through the mesh. All the fish will pass parallel to the mesh. The problem here is normal is like this, motion is like this. These two are in perpendicular direction. Dot product is 0. A dot B cos 90. Whereas when the mesh is like this, normal to the mesh is like this, motion of the fish is like this, theta is 0. So cos 0 gives the maximum answer. You can catch maximum amount of fish. Whereas if you place the mesh like this, then the number of fish passing through the mesh will decrease, and all the fish will not pass through the mesh. So as the angle increases, when theta increases, cos theta value goes on decreasing. So, but you have to remember, throughout in second PU or in anywhere, whenever we come to, we get an opportunity of using area as a vector, we take the normal to the area, not the area along the area. This is not the direction. Direction is normal to the area. Maybe a coil rotating in a magnetic field, then normal to the area is taken as a vector. Okay. So, define electric flux. If you are asked to define electric flux is defined as the number of electric field lines crossing the surface normally. Crossing a surface normally. This is only definition, but remember, this cannot be mathematically calculated like this. You can't calculate how many electric field lines are crossing, because electric field lines itself is an imaginary quantity. So number of electric field lines, this is number of electric field lines crossing a given surface normally is called electric flux. So if they are not normal, get the component. If the electric field lines are not normal to the surface, get the component in the normal direction. That is E cos theta. E delta S cos theta. So that is one question. Define electric flux. Number of electric field lines crossing normally through a given surface is called electric flux. And how do you measure electric flux? It is the dot product of electric field and delta S, or E delta S cos theta. What is theta? Theta is the angle between these two vectors, E and delta S. So formula for electric flux is the dot product of E and delta S, or E delta S cos theta, where E is the electric field strength and at that point, and delta is the areas of the surface, and theta is the angle between these two vectors, electric field and delta S, or the direction of electric field and normal to the surface. That angle is theta. And is electric flux a vector quantity? No, it is a scalar quantity, because it is a dot product. The result of dot product is a scalar quantity. Now, what is the SI unit of electric flux? Electric flux SI unit is delta phi is equal to, we know the formula. Once you know the formula, you can write the unit. What is electric field? Newton per coulomb. What is surface area? Meter square. Cos theta, mathematical function, it has no unit. So SI system unit of electric flux is Newton per Coulomb meter square. So remember this formula always. And remember, this theta is the angle between normal to the surface and electric field, not the surface and electric field. That is very important, because in the examination under pressure you will forget it. So you have to make it very practice every now and then. Okay, now, sir, if you are given this surface area, you can choose any area and you can find out the flux. Now, suppose you want to find out what is the full flux emitted by a charged body. In order to do that, we have a method, and that is given by Gauss. I'll take another paper and explain what is Gauss law. Now, and this is also based on an imaginary concept. Okay, Gauss law. What does Gauss law say? G-A-U-S-S, Gauss law. Now Gauss says you need not take a small area and find out how many electric field lines are passing normally through that area. You can do one thing. Find out the full flux. I will give you a formula, or I will give you a law. According to the law, find out the full flux. Now how do you apply that law, or how do you find out the full flux emitted by, or the total number of electric field lines passing through a given area, or given by a charge? So how to find it out? And this is Gauss who gave the law, Gauss law, very important law. It is highly theoretical. Of course, you have to, this is the first time you are finding a law like this. So I can give you a equivalent theory for that. Just in our day-to-day life, you can assume it like this. Suppose you take a bulb. Same, you will go to the same case of the bulb. It emits rays. This is what we assume, and diagrammatically we can represent it like this. But you can't see a ray of light around a bulb. That is only assumption. And I will say that this bulb is very bright, and I will show it by drawing many lines, rays of light like this. Now, sir, what is the flux here? Okay, take a paper and keep it here. That is the flux. How much light falls on this, and how many rays of light pass through this. If you keep the same area here, only one ray of light passes through this. This is only just example I have taken. You can't count the number of rays. There is no limit for the thickness of the rays of light. So the flux keeps on changing as you move away. Now, can you calculate what is the total flux emitted by this luminous flux of this bulb? That is very easy. What you have to do is, you take such on these small areas, here, like this. Take all such areas and cover the whole bulb. Of course, this should be three-dimensional. You have to cover from this side, inside, everywhere. Cover this whole bulb, or keep this bulb inside an imaginary balloon like this. You keep it inside an imaginary balloon, this bulb. Now, definitely, all the rays of light should pass through this balloon, correct? And they can't escape. Sir, what should be the size of the balloon, sir? Of any size. Or imaginary bubble, or imaginary sphere, glass sphere, say. All the rays of light should pass through this balloon. No light can escape without passing through the balloon. It should pass like this. So, if you want to calculate the whole flux emitted, or luminous flux of this bulb, you have to enclose this bulb within a sphere. Sir, suppose if I have put the same bulb inside a cube, what would have been the total luminous flux of the bulb through this cubical box? So now the bulb is within the box. So box is like this. What is the flux through this box now? Is it same as this one? Definitely it will be same as this one, because what are the rays of light? How many rays of light have started from the bulb and passed through this sphere, imaginary sphere, that is balloon or any bubble? Same rays of light should pass through this box also. There is no doubt. All because source is same. So flux depends on the source and not depends on the enclosure. Whereas here it was depending on the surface area, but now we are enclosing it. So whether you enclose this bulb within this imaginary balloon or a bubble, or whether you enclose the same bulb in an imaginary cubical box, whether you enclose that bulb in an imaginary pyramid like this, the same bulb here inside the pyramid, same rays of light should pass through this pyramid, same rays of light should pass through this cube, same rays of light should pass through this sphere. Or even if you take a larger sphere, same rays of light should pass through, isn't it? If you increase the size of the sphere, the same rays will pass through. Suppose this passes a certain number of rays of light, same rays of light should pass through this sphere also. That means if you are calculating the total flux, I am not calculating a flux through a small area like this, total flux, then you have to enclose that source of light within an imaginary shape, three-dimensional shape, that is closed shape. That may be a sphere, larger sphere or smaller sphere, or a cubical box or a cylinder, pyramid or a cylinder. Wherever you place that bulb, the total rays of light passing through all the enclosures are same. That is what Gauss said. Gauss says, if you want to write the total flux, so this is what Gauss says. If you want to write the total flux of any source, enclose that source within a closed surface. It should be a closed surface, remember. It should not be an open surface. Then the total flux can be given by a formula. Of course, now we will switch on from a luminous flux to electric flux. Okay, I have a charged body and I can imagine electric field lines starting from the positive charge ending at infinity. There are limited electric field lines, say. Okay. Now, how many electric field lines pass from this charged body? If I want to imagine it, place that charged body within a sphere. All the electric field lines should come out of the sphere. Place that charged body within a cubical box like this, or at the center of the cubical box like this. So what is the amount of electric flux through this cubical box? Same as this one. It cannot be different. So flux through all the enclosures are same. Now the Gauss law goes like this. So what does Gauss law say? Flux through any closed surface. See the difference. Flux through an open surface. Flux, that is E delta phi cos theta. Delta phi is equal to E delta S cos theta. We have written the formula to that. Flux through any open surface, not closed. Delta phi is equal to E delta S cos theta. Now Gauss law states like this. It is like this, Gauss law. We have written 3 times Gauss law, but not even defined even once. Okay, now we will define it. What is Gauss law? Flux through any closed surface, say a sphere. This is a charged body. The total flux through this imaginary sphere, which you have imagined that it is enclosing this charge. Total flux through, this sphere is 1 by epsilon naught times, suppose you have kept it in vacuum, 1 by epsilon naught times the total charge within this sphere or within this enclosure, and I call this as Gaussian surface, Gaussian. Okay, Gaussian surface. So Gaussian surface can be anything. We have told already that you can place the bulb inside a sphere, inside a cube, inside a cylinder, inside a pyramid, inside anywhere. The total rays of light coming from the bulb should be same because it depends on the bulb, not on the enclosure. Similarly, when a charge is enclosed by a closed surface, it should not be an open surface. When the charge is enclosed by a closed surface, total flux is 1 by epsilon naught times the total charge within the Gaussian surface. So Gaussian surface is an imaginary enclosure which encloses the charge, and the total flux coming out of the this enclosure is 1 by epsilon naught times the charge. So Gauss theorem is stated like this. Total flux through any closed surface. So flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed within the surface. Right? So total charge enclosed within this surface is Q. So formula is 1 by epsilon naught times the charge. So this formula and this statement are very important. See, last time I was using delta phi because I was taking only an open surface. What is the flux through this? That is the number of electric field lines passing only through this surface. Now I have enclosed completely. Total area I have taken. So that is why it is not delta phi, it is phi. For delta phi is E delta S cos theta. It is a smaller area. Now it is a full area. So flux through, so this formula statement are very important. So state Gauss law. Flux through any closed surface is equal to 1 by epsilon naught times the total charge enclosed within the surface. So flux through any surface, closed surface, is 1 by epsilon naught times total charge Q. Total charge in the sense, suppose you have many charges here inside, Q1, Q2, Q3, many charges enclosed within. You have to write the total one, total charge. So this is the enclosure, and remember here, this formula or this statement doesn't say anything about what type of enclosure you should have around the charge, isn't it? That is because we have already seen whatever be the shape of the enclosure here or here or here, we have just scribbled it like anything here, like a kid draws a diagram. We have seen this. Flux through any enclosure is the same. So never mind whatever be the enclosure. So just worry about what is the charge inside the enclosure. What is the bulb kept inside, not the enclosure. So that means, suppose I can remember one question for the entrance exam now. A charge Q is enclosed by two spheres, two imaginary spheres of radii r and 2r. What is the ratio of flux through them? Same charge Q is enclosed by two spheres, imaginary spheres. They are Gaussian spheres. What is the ratio of flux through them? Same bulb is covered by two spheres. One radius is r, another radius is 2r. But whatever the rays of light passing through this smaller one should pass through the other one. How many electric field lines pass through this inner sphere should pass through the outer sphere also. So ratio of flux through the two spheres is 1:1. It cannot be 1:2 or 2:1, something like that. It is same. So that is why flux through the closed surface does not depend on the shape or the size of the enclosure. So Gaussian surface, what you call the surface which is enclosing the charge, does not decide what is the flux. It is the source which decides the charge. Total charge within the Gaussian surface which it decides the charge. So flux through, it should be a closed surface for Gauss theorem, and it should be the total charge here. These two are very important, and it does not, so we don't get anything identification here about the size of the Gaussian surface and what is the shape, whether it is a cube, whether it is a cylinder. We are not worried about this. We are worried about the total charge within the Gaussian surface. So this is a very important theorem, and we are going to apply this, and we can use both the formulas. One is flux through a small area where that area is held like this. Suppose the normal is like this, theta. Delta phi through a small area is E delta S cos theta, and the another one is Gauss theorem, which gives the flux to the full closed surface 1 by epsilon naught times the charge enclosed. So that's about Gauss theorem. Thank you.